Hi, everyone. Thanks for coming. I'm Lea Verou. If you've ever heard my name before, it's probably due to one of my open source projects, some of the most popular of which are Prism, Doublet, Prefix-Free, CSS3test.com, and there are many others on my GitHub page. I used to work for W3C until last August, and I'm still an invited expert in the CSS working group. These days, I'm writing a book for Riley about CSS. And in September, I'm going to change my life quite a bit, and I'm going back to school. I've been accepted to the PhD program at MIT in computer science. So, enough about me. Let's move on to more interesting things, like how color works on screen. So this is a white pixel, or this is how most people imagine a white pixel. Most people imagine that pixels are these little squares on our screen that have like millions of different states for the different colors. But the reality is actually a little different. A white pixel, if you zoom in enough, it looks more like this. And these three regions are called subpixels. And actually, in our LCD screens, it looks more like this. And you might be wondering, how is this a white pixel? This is just red, green, and blue. I don't understand. Where's the white? So yeah, if you look at it in such a big size, yet it looks like three different colors. However, if you start going further and further away and zooming out, the colors start blending in. Your eye starts blending the colors in, and it starts looking like white. And obviously, this is not a very sophisticated CSS animation, but you can see how these colors start blending together to create something that looks like light gray. And in reality, in our screens, it looks like bright white. And to create the different colors, different subpixels light up, and each of them has a number of states, actually 256 different states. So their combination creates all the different colors we see, which is why RGB is called an additive color model, because if you combine all its different components together, you get white. As we'll see towards the end of the talk, there are also subtractive color models that work differently. So I showed you the subpixel geometry of a common LCD screen, which looked a bit like this. But this is not actually true for every kind of screen. Many different types of screens have a different subpixel geometry. You can see here that a CRT screen has a different subpixel geometry than an LCD screen, even TV CRTs have a different subpixel geometry than PC CRTs. But I think the most interesting one is this one, the XO1 LCD, which is just a code name for the project One Laptop Per Child, the $100 laptop that was going to be distributed in poor countries, and I think it has been. So these are not actually subpixels. These are every pixel of that screen is a different color component. And depending on how they light up, it gives the illusion of a much larger resolution. And what I found really interesting is that its resolution actually depends on the angle that you look at the screen. And actually, even LCD screens of different devices have different subpixel geometries. For example, here you can see different iPad models. Let's hope I will not need much Wi-Fi because I can't join. Here you can see the subpixel geometry of different iPad models compared to the iPhone and compared to another model, an ASUS E Pad Transformer Prime. And you can see that even those are different. So let's go back to our friend, the subpixel. Generally, everything I'll say today has its exceptions, but generally each of those subpixels is 8 bits, which means you need 24 bits per pixel, which means that in an uncompressed image, every pixel needs 3 bytes. So it's a quite interesting exercise to get an uncompressed image format, like a bitmap file, for example, and try to multiply the width by the height by 3, and it's really close to the actual size of the image, not exactly close because of metadata. And this means that you can have 256 to the third possible colors, which is something like 16.7 million. So quite often, we need to display things like vectors on the screen, especially when we're displaying fonts. Every font is a vector file. So they don't fall exactly on whole pixels. So here, for example, I have this diamond. And as you can see, not all of it falls on whole pixels. Some of it, for example, here, it falls on half pixels. So how would we display that on a screen? One way to do it is to dim every pixel according to how much it's covered. So if the pixel is 50% covered, in this case, the shape is white. So according to how much it's covered, we dim all of its subpixels by the same amount. So since this pixel is covered completely, you can see it here, it becomes completely white. But this one is more like a 50% sort of gray because it's only covered by 50%. And that creates a pretty decent result, which is why Apple computers use that to display fonts, even today. There's another sort of anti-aliasing which tries to triple the horizontal resolution of the screen by using the subpixels, by lighting up different areas of the subpixels based on where the shape we're trying to display falls on, which you can see here. So as you can see here, not all of the subpixels are lit by the same amount. The blue one is lit 100%. The green one is more like 50%, and the red one, you can barely see it. Because if you remember, the diamond shape we had covers the pixels like this. And this explains why, if you looked closely enough at fonts on Windows, you could see these colored pixels at their edges. And you might be wondering, like, my font was black. Why do I see blue and orange and pixels like that? Because I just had a black font. So the reason this happens is subpixel anti-aliasing. If I press A here, you can see how the text falls on the different subpixels. Let's change the text to something more interesting. You can see how each letter falls on the subpixels, and if I go back to how this appears when you're zoomed in, you can see how the different colors change because those subpixels control what color is generated. So this is a little about how colors are displayed on screen. However, most of us, I presume, are web developers, and we care more about how color is displayed on websites. So additive color, the RGB color model, like I explained earlier, is a combination of 3 coordinates, and this is commonly displayed as a cube, where the x coordinate is red, the y coordinate is green, and the blue coordinate is z, which is quite useful for a number of things, like, for example, calculating a very rudimentary measure of the distance between 2 colors. You can take the Euclidean distance between the 2 points in the cube. And you can see how the cube looks if I do this, which actually took me all night yesterday to code this with CSS. So I do not advise you to try something like that. But I quite liked it. So because when we're picking color on screen, we can't obviously use a cube. There were some attempts for 3D color pickers, but they weren't quite successful, because obviously, even if I could click on this cube and pick a color, it's not exactly practical, is it? So usually, on the screen, we try to flatten 3D coordinate systems into 2 dimensions, or even 3 single dimensions. You probably have seen these color pickers that are 3 sliders with a gradient like this one, which basically show you the 3 separate coordinates, but the best ones are the ones that only flatten one of the coordinates and still show you a plane of all the possible colors that can be generated by keeping, for example, red constant. Here, if I set red to, for example, 255, you can see all the different colors that I can generate by this. And you can even change the coordinate that you keep constant and see all the possible colors that can be generated. Or even blue. However, if you notice something here, this is not exactly intuitive. Like, every edge of this square is a different color, and it's not exactly obvious how we go from one color to the other. We don't usually describe colors to other people. If, for example, we want an orange, I know, because I remember it, that it's something like red and a little green and no blue. But you don't describe orange like this. Hey, I want some red with a ton of green and no blue. That's not how we think, which is why RGB is not a very author-friendly way to specify colors, which is why we got more color formats, and we will get even more color formats in CSS Level 4, as we'll see later in this talk. But before that, let's go a little to the past and remember how colors were in HTML 3.2, where developers had it much worse than we did when we started, unless you started back in 1997, which I'm sure many of you did. So back in HTML 3.2, the only color formats you could use is hex colors, which, as you know, the first component is red, the second one is green, the third one is blue, and this color actually means this one, which looks like this. It's my favorite color. And, well, it's close to my favorite color, not exactly. But this is even less intuitive than the RGB color model that we saw already, because we don't just have to combine red, green, and blue to create the color we wanted, but we also have to convert decimal to hexadecimal. And nobody, imagine thinking, so, okay, we have 255, which is FF, and then 0, which is 0, 0, and then what about 90 that we had for blue? Yeah, that should be 5 times 16 plus 10, so this is 5A. So yeah, there's my hex color, FF005A. Nobody thinks like that, ever. We wouldn't even use JavaScript, which is really easy to do in the console to convert from hex to decimal and vice versa today. We can just use a line of code and do it. And there are actually 2 easy methods to do it for hex to decimal. Most people use this, but this is actually much easier when you're just using the console. However, most people didn't do that. Most people had a hex color that they pasted from a color picker, and then because we were lazy to go back to the color picker and to change it, we tried to hack it like, yeah, I want to make this darker, so I'll just remove 22 from every component, so this will become 77, this will become 88, and then I'll get something that's slightly different. Yeah, it's darker, but it's not exactly the color I wanted, so then we end up fiddling with the color coordinates, and it's a complete mess. And yet, we developed such an attachment to hex colors that even today that we can use alternatives, we still insist to hex colors for some weird reason, just because we're so used to them. And of course, we got these color names that are mostly useless. Does anybody actually know where these color names come from? They came from the Windows VGA palette. If you restarted your Windows in safe mode and it was a 60, and the screen could only display 16 colors, it was these colors, if you remember those days. So basically, in HTML 3.2, we were quite screwed. We only had hex colors, confusing and cryptic, and color names, which are mostly useless. So then we got CSS, which we actually got at quite the same time in 1997, but it took several years to catch up because browsers wouldn't support it. And we didn't really get many more colors between CSS 1 and CSS 2.1, which is why I have them together. So in CSS, we got a slightly nicer format to describe colors. This is the same color we saw earlier. And finally, we could adjust the different coordinates in decimal, which was quite an improvement. It was still a really confusing color system, because humans, like we said, don't think like this. Like to specify a sort of light of dark gray, you had to think, yeah, I want all coordinates to be the same, but sort of dark, so let's use 100 for all of them. And yeah, now we have a gray, and maybe if I want to make it a bit bluish, I'll increase this, and that's still quite confusing. We also got percentages, which nobody ever used for, I don't understand why, because they have exactly the same support. I think it's because hex colors taught us to think in powers of 2, from 0 to 255. So we transferred that knowledge to using the RGB function. So instead of doing things like this, we still insisted on using numbers from 0 to 255. And we got 3-digit hex colors, which were a nice way to describe some hex colors. If you had a hex color that looked like this, you could shorten it to F06. So, for example, you could specify black with just 4 characters, or white, or a number of other colors. And we got a new color name, orange. Isn't that the most useful thing we got in CSS? So, to sum up, in CSS 1 to 2.1, we got RGB, the RGB function, better but still quite confusing. We got the shorter hex format, shorter but still confusing. And we got the orange named color. I actually made a game that you can play at home. Originally, when I made it, I was planning to play it during the talk, but soon I realized that this is quite impossible, because you can't really do this on stage. Even if I try, it won't quite work. But it's not as hard as it looks here. So you can try it at home, and you can compare your timing when you're trying to solve it for RGB colors and for other color formats that we'll discuss soon. OK, now I must stop playing this. It is quite addictive. But OK, I need to move forward. And then we got CSS Color Level 3. Notice I didn't say CSS 3, because such a thing does not exist. After CSS 2.1, CSS was split into multiple modules, and it became this huge thing. And now we have like 70 modules, so each of them has its own versioning, because imagine a specification that needs to move forward, and it has that much stuff in it. It would take ages. Like, there are still things that people consider CSS 3. There are still drafts, and there are things that are recommendations. CSS Color Level 3 is one of the ones that are recommendations, which is why work has already started on CSS Color Level 4, which has an amazing number of cool stuff, not all of which will happen, but even if half of them do, we'll be much better off about color. So before I move into what we got with CSS Color Level 3 and finish this historical, this remembering of historical events, here's a simple JavaScript class. And notice the quotes. I did not say JavaScript class, because I know that there aren't exactly classes in JavaScript. But let's say, because it works in a similar way as classes do in other object-oriented languages, let's call it a class just for simplicity. So this is a class to generate color objects. And here it doesn't really do much. It accepts an array of red, green, blue, and transparency to create an RGB color. And it also has a getter and setter in cases you only need to work with RGB without the alpha component. And it has a getter and a setter for convenience when you want to get the alpha. So this is not particularly important now, but we will refer to this class throughout the rest of the talk and add methods to it that actually do something. So try to remember a little bit how it works. Basically, you create colors like this. If I wanted to create a magenta sort of color, I would call it like this, or I could just create an empty color, have it get the default parameters, and then assign an RGB array to it. And here's how we would add methods. We would, for example, if I wanted to add a method that inverts the color we have, I would add an invert method to its prototype, go over each of the RGB components, and replace it to the same component subtracted from 255, which is how you get the inverse of an RGB color. So back to CSS Color Level 3. We got a system that's much easier for developers, that's much easier for humans to describe colors. Because, let's go back to the orange example. You don't say, I want a color that's red and has some green in it. That's not how you think about colors, especially since when we were children, we were playing with watercolors, we learned that red and green actually create brown, so what the hell? So we got another system with 3 coordinates. One of them is hue, which is just the very basic color. It doesn't matter whether it's muted, whether it's dark, nothing. It's just a basic hue. Does it lean towards orange, towards fuchsia, towards blue, towards aqua, towards green? What's the basic hue? And then there's saturation, which is how gray it is. 0% saturation is completely gray. It doesn't even matter what hue it has because it's completely gray. And as you move towards the edges, it goes away from gray. And lightness, which is how close it is to white or black. So you can see here that, for example, if I want to pick a bright orange, it's much easier to know that I want a bright color, so I need to avoid the gray center and go somewhere towards here. And it's much easier to see, oh, I want it closer to red. Oh, no, I want it closer to yellow. And this is not because of this is a graphical color picker. Even with the numbers, as long as you learn the basic hues, it's much easier to think about them that way. And if I want a dark orange, then I can just adjust the lightness. And if I have this shade of orange in my website and I want darker and lighter variants, I can just change the lightness. And the corresponding color function in CSS looks like this. This is the orange we picked earlier. The basic thing you need to remember is that if you have a saturation of 100% and a lightness of 50, the only thing you need to remember to use HSL is the basic hues, which are, there are 6 basic hues: 0, 60s yellow, 120s green, 180s aqua, and so on. Apart from that, you can figure out everything else just by thinking of how HSL works. For example, if I want a muted aqua, I'll just reduce the saturation. There it is. If I want a darker aqua, just reduce the brightness, the lightness. And like I said earlier, RGB is often displayed as a cube. Contrary to that, HSL is actually displayed as a cone. HSL is just a transformation of RGB into cylindrical coordinates. It's exactly the same color space, just with different coordinates. And the reason it's not depicted as a cylinder, you will see it on the web as a cylinder, but you will also see it as a cone, as a double cone, actually. This is just half of it. The reason for that is that as you move towards a lightness of 0 or a lightness of 100%, you get fewer possible colors. And when you're at lightness 0, it doesn't matter what hue or saturation you have, you can only get black. Similarly, when you have a lightness of 100, you can only get white. It doesn't matter what the other coordinates are, which is why it's depicted as a cone. And yeah, you can try here to play with HSL and see how long it takes. It will be much shorter. And the cool thing about HSL and knowing how HSL works is that you can also use it for SVG filters, which in WebKit and in Blink and WebKit you can use with that syntax. In Firefox you need an SVG filter, so I'm showing them in Chrome because it's just more elegant with that syntax. So here I had this baby and I applied a hue rotate filter to it. So now every single color in this has its hue shifted by 60 degrees, which is incredibly useful if you specify, for example, a sepia filter to make it sepia, which is basically sort of close to grayscale, but yellowish. So then you can saturate it to make it to increase its saturation. And then if you apply a hue rotate filter, you can basically colorize it to any color you please. 120 would make it more closer to aqua, because remember, yellow is 60 degrees. So 60 plus 120 is 180, which is the hue of aqua. Similarly, if you add 180, you get blue. Unfortunately, Firefox doesn't support this simple syntax yet, but it's coming really soon. However, even though developers were raving about HSL when it first got introduced a few years ago, soon we discovered that it's not the best thing since sliced bread. It has its own shortcomings, which are based on the fact that it comes from RGB. It's basically RGB. It's lipstick on a pig. So here you have yellow expressed in HSL coordinates and blue expressed in HSL coordinates. Do you see what's wrong here? Both of them have a lightness of 50%. Do you think they're equally light? Blue is obviously much darker than yellow, and yet this is not reflected in HSL. HSL thinks that they're exactly the same lightness. The reason for that is that RGB is not perceptually uniform. We say that a color space has perceptual uniformity when the perceptual similarity of two colors is measured by the distance between them. Remember the RGB cube in the beginning. If RGB was perceptually uniform, we could calculate the distance between two colors just by getting the Euclidean distance of 2 points in the cube. However, that will not give us very good results. And HSL is not perceptually uniform either because it's just a transformation of RGB. You can see the same phenomenon in RGB coordinates. Both of these colors, both the first and the third color, have the same distance from the middle one. However, the first two seem much more similar than the second to the third one. And they have exactly the same... Stop animating. They have exactly the same... okay, this was cool once, but now it's not. So as you can see, fuchsia, which was the middle color, is somewhere around here. And then the top color is somewhere around here. It has a distance of 128, because the side of the cube is 256. And the other one, the third color, is here, and it has a distance of 128. However, you can see that their distance visually is not nearly close to their geometrical distance. So if we wanted to use the lightness, the HSL lightness, to determine, for example, if we need to color our text black or white, if we didn't know what color it's going to be on, and we thought, hey, I'll just check the lightness of the color, and accordingly, I will color my text black or white. As you probably suspect by now, that wouldn't work. And the reason is that the HSL lightness is defined like this. If we wanted to add a lightness getter to our class, this is how we would code it. We would get the maximum of the RGB coordinates, the minimum of the RGB coordinates, and then we would find the average. And because that would be in the 0 to 255 range, we would change it so that it's in the 0 to 100 range, but that's basically how you calculate it. You get the average of the maximum and minimum. So as you can see, this doesn't account for the fact that our eyes are much more sensitive to blue than they are to red, than they are to green. RGB green is much lighter. We see it as much lighter than we see blue. The good thing is we can calculate something called relative luminance, which is not perfect, but it's much closer to how we perceive colors. And I don't expect you to memorize or even read the whole code here, but I just included it to show you that it's not something hugely complicated like finding derivatives of stuff or anything. It's just a few simple mathematical operations, and then to convert each component to a different scale, and then you return a weighted average. So blue is multiplied by a much smaller number than red, which is multiplied by a much smaller number than green. So relative luminance accounts for the fact that each of these three components are perceived with a different lightness. So here I've made a slide that compares these two methods. You can see, for example, the luminance and the lightness of gray. And you can see that gray is actually darker. It's actually closer to black than it is to white, which is reflected in the luminance. If we specify blue, you can see that the luminance is 7%, and the lightness, of course, stays 50%, like we saw earlier. And yellow has a luminance of 93%, which is much closer to how we see it. However, this is still not perfect. If I specify an orange color, luminance is 48%, even though it should be higher than 50%, because obviously black would be much more readable on orange than white is. But it doesn't fail as spectacularly as HSL does, which is why it's used in the definition of color contrast in the web accessibility guidelines, that if you work in a government organization or a corporate thing or something like that, you might actually have to follow. Like when I was working at W3C, I had to research color contrast because I had to pass, when I designed something, it had to pass WCAG 2.0. So this is the formula for color contrast. As long as you've calculated luminance, it's pretty simple. You just get the ratio of the two, assuming you divide by the smaller one of the two, and you just add a small amount, 0.05, just so that you don't end up dividing by 0. So it's basically a ratio of the two luminances. And when I was working at W3C, and for the first time in my life, I had to follow contrast ratio rules, I found that all the contrast ratio tools available only accepted hex colors, or they required you to painfully move sliders to match an RGB color, which was even worse, because I had the colors in my CSS file. I wanted to copy them and see what the color contrast was. Of course, there were tools that calculated the color contrast of your whole page, but they weren't particularly smart. So I made this to calculate the contrast ratio between any two CSS colors, so I could just copy and paste them. And even semi-transparent colors, which no other tool supported. And even though semi-transparent colors are pretty easy when it comes to overlaying them on a solid, on an opaque background, it becomes more tricky when you overlay them, when you overlay a solid, an opaque color text on an alpha transparent background, because then obviously the contrast you get depends on what's behind the semi-transparent color. So there is no single contrast value. It's a range depending on the possible contrast ratios you can get. And the smaller your alpha transparency, the bigger the range. So if it's 0.2 here, it's basically a range of almost every possible contrast ratio you can get. The full range, by the way, is 1 to 21. But it worked quite well, and I could use arrow keys to adjust my values until I matched a decent ratio. And this brings us to semi-transparent colors, which I haven't actually discussed yet. With CSS Colors Level 3, we also got semi-transparent colors, which are just an extension of the two color formats we have, RGB and HSL, with an alpha parameter. So, for example, here, without the alpha parameter, I have black. Unfortunately, to go from RGB to RGBA, I have to change two things, which was not a good idea. And in CSS Color Level 4, that will change, and I'll be able to add we'll be able to add a fourth parameter in RGB, like this. But for now, we have to use a different function name, and we can have semi-transparent versions of any color, and we can have semi-transparent colors of HSLA colors. You can see how that works here. And they could be 10% opaque or 90% opaque or anything. However, have you ever wondered how these alpha transparent colors that we're so used to using are actually displayed on screen? Because our screens don't have semi-transparent colors. What would we see there? The back of our screen, like the circuits in our laptop? So this alpha transparency is just an abstraction. At the end, everything needs to be composited on to be displayed on the opaque pixels we have. Remember, the pixels we have only 3 components, red, green, and blue. They don't have any alpha. And this is done with a process called alpha blending. And the algorithm for this actually predates our color screens. It was discovered in 1984 by Porter and Duff, which they also discovered. They also defined lots of other operators about mixing images. Alpha blending is basically the over operator. So assuming we add an over method to the class we already have that accepts another color object as a parameter, and we want to overlay the current color we have over the other color that could also be semi-transparent, and in turn, it would need to be composited as well. Obviously, our screens don't use JavaScript for this, but I figured it's the language that most people are familiar with. And it works, in a simplified way, it works a little like this. Every color component is multiplied by our element's alpha transparency, and then we add the the same color component from the other color multiplied by its own alpha, multiplied by 1 minus the alpha of the first color, because that changes how much of the color underneath we can see. So it needs to be factored in. And then at the end, obviously, our alpha changes. So if we have, for example, a color at the top with 50% alpha, and we overlay it on a color with 25% alpha, obviously we get a color with a higher alpha at the end, which is basically our original alpha plus this, the alpha of the second color multiplied by 1 minus the alpha of the top color. A similar but simpler algorithm is when we want to average two colors. And by averaging, I don't necessarily mean the color that would be in the middle, but for example, something that's 30% yellow and 70% red. It could be a weighted average. So this is called color interpolation, finding the intermediates of two different colors. And assuming we wanted to add a method called mix in our color class with a second color object and a weight that should be optional, it should default to 0.5, then we would just go over each of the coordinates we have, and we would get the weighted average between our original color and the second color. If you're using a preprocessor for writing CSS, for example, if you're using SASS, you can do the same thing with the mix function that's built in. And it works in pretty much the same way. Color interpolation is really useful when you're doing gradients, and it's built into the browser. So in CSS, we have gradients that look like this. We also got them in CSS Images Level 3. And it's quite easy to figure out how the gradient should look when you have two opaque colors like this. However, when you have an opaque color to a transparent color, things get a little trickier. So if I try to have a gradient, let's change the text color as well. Much better. So if I have a gradient from white to transparent, the result is not quite what I would expect, and it becomes more obvious if I also add a white background color. Since I have a gradient from white to transparent on white, what would I expect to get? I would expect to get plain white. It's just white on white, right? So why do I have all this gray in the middle? The reason for this is that transparent is actually a shorthand to transparent black. It's not a magical transparent keyword. It's just transparent black. So as I'm transitioning from white to transparent, and our alpha is changing from 1 to 0, our actual color is also transitioning from white to black. So I can see the gray tones it goes through. For example, in the middle, I would get 50% transparent gray, which is why I can see these colors. So in the beginning, browsers that did this were actually conforming to the spec, and then we noticed that, hey, this is not right. People are doing gradients from a color to transparent. They're expecting to get a gradient from the colors they specified to the transparent version of the color they specified, and not to transparent black. So it needed to change. And it turns out there's something called a pre-multiplied RGBA space, where every color is stored multiplied by its alpha. So you can't have transparent black anymore, or even transparent white or transparent red. You just have transparent. So when you interpolate between an opaque color and transparent, you get what you expect. Chrome already does this. IE already does this, but I'm using Firefox here, and it doesn't. So to get the result we expect in Firefox, we need to provide the transparent version of the color we're actually transitioning from. So if it's white, we need to provide transparent white. So in this case, I've used HSLA to provide transparent white. And you can see these side by side to see the difference. And I think this makes it even more obvious how much of a difference this makes. And lastly, in CSS Color Level 3, we also got more named colors. Yay. So the problem with these named colors is that, as you can see in this distribution, they're not exactly evenly distributed. Also, in most cases, they're not exactly practical, because they're longer than using an RGB or HSL notation. In other cases, they're just weird. Who would expect that these would be color names and they would have these colors? Old lace? Seriously? Goldenrod? There are also the color names that are plain racist. And there are also color names that are just insane. I'm not making this one up. The reason for this insanity that had many developers wondering, WTF, is that we got gray in the first days of having named colors, which, as I said, came from the Windows VGA palette. So we already had the gray color name. That couldn't be changed. The other color names were adopted from the X11 color palette, and gray there had a different meaning. And it was actually lighter than this dark gray. But we couldn't change the gray we already had, so we just adopted dark gray as it was, and gray remained as it was. So we ended up with this insanity. We also got, however, a really useful color name that most people are unaware of. You've probably noticed that if you don't specify a border color, if you specify a border color, you obviously get something like this. But you've probably noticed that if you don't specify a border color, you get the same color as your text. And you can even change your text color, and that adjusts automatically. Many other properties have the same behavior. For example, box shadow. If you specify a box shadow without any color, it gets the text color by default. Or if you specify a text shadow without a color, it just gets the text color, which can sometimes even be useful for doing like glow effects. And there's a number of properties with this. There's a number of CSS properties that do this. And in CSS 2.1, these properties were defined as special cases. If there's no color provided, you get the color of the text. In CSS Color Level 3, we got a special color keyword to do exactly this thing. And it's called current color. We adopted it from SVG. It already existed in SVG for many years before that. And current color does exactly this. So now we can say that by default, that the initial value of the border color is current color. It's not a special case anymore. It's just an initial value like any other. And the good thing is, you might be wondering, OK, we already had this behavior. How is it useful? The good thing is that we can use current color in other things now. We can use it everywhere a color is accepted. So for example, assuming I wanted to use CSS gradients to create a background of scan lines, for example. So let me add a linear gradient from current color to transparent and bring the color stops together and make the background size smaller. Even smaller, that's too big. So now this is basically the sort of background I wanted. I can even make the lines a bit thinner. And if I change the text color, for example, let's change it to my favorite color, this sort of pink, you can see that it adjusts automatically. And this is a very simple case and arguably not very useful, but there are many cases where I can just specify a text color once, and then I can use current color to avoid repeating my text color, the color I'm using for the text in other places, which makes for more flexible CSS. The least places I have to change something to change the appearance of what I'm styling, the better. It keeps our code much more dry, and it's basically the first CSS variable we ever got. We will eventually get proper CSS variables. I know developers have been asking for them for like over 10 years, and they are coming. There is a spec about this. It's still in draft, and even though there are experimental implementations in browsers, in Firefox and Chrome and Safari, I think, now we're discussing about changing it again, changing the syntax again, but it will eventually make it. Once we started getting implementations, that's it. It will eventually come. But until then, this is the very first CSS variable ever. And it's useful in a number of cases. So to recap, in CSS Color Level 3, we got HSL, which is better, but as we saw, it's not great. We got semi-transparent colors, which are badly needed. More color names, still mostly useless. And current color, which is cool, but obviously quite limited. So now the cool part, and the least useful one, because they're not implemented anywhere. But I still think it's really interesting to know what's coming and get excited about it, and even push browsers. Hey, implement this, I really like it. That's how browsers end up implementing stuff. The developers push for it. So in CSS Color Level 4, and keep in mind, everything I will say in this section is very tentative. The syntax might change. The syntax will probably change. Probably some version of these things will make it, but maybe not in the same syntax. But currently, they are in the draft specification. So one thing is, and this is one of the most certain things, gray will become a function. So the gray keyword will be equivalent to the function with 50% as a parameter, which is equivalent to RGB 50%, 50%, 50%, or HSL with 0, 0, and 50%. It's just a shorthand. And we can just change the first parameter and create any sort of gray we want, from black to white. And we can even provide a second parameter for the alpha, to have semi-transparent grays, which are like 50% of the colors we use these days. The good thing is we can have gray today with SASS with exactly the same syntax as will eventually make it to CSS. We can just specify a one-liner function that looks like this, and then we can use gray in exactly the same way, with percentages or with numbers from 0 to 255, which I forgot to mention, or with an alpha parameter, and SASS converts it into a format that current browsers understand. So this is something we can use today if we're using preprocessors. We will also get 4 and 8 versions of hex colors, which are basically the same as their 3 to 6-digit counterparts, but with an alpha parameter. Because developers have been asking for them for so long, because developers are used to using hex colors, and they didn't like that they had to change them into RGB or HSL to make them semi-transparent, which is sort of crazy if you think about it, because hex colors are the least understandable of color formats. Like, for example, if I have something like this, I'm just typing random numbers here, but let's say I have something like this, and then I give it a 50% alpha. How is this color understandable? Who knows what this does? It looks like a serial number from something. But it will come, and it's also one of the most certain features that will make it into browsers. We will also get a color function that does all sorts of things. It can adjust colors to make them lighter by mixing white with them. And this is even more useful when you think that CSS variables are coming, because you'll be able to use a variable here. And there's also shade that makes the color darker by mixing it with black. Obviously, 100% is complete black. And there's also blend, which mixes it with another color. Remember when I showed color interpolation earlier? This is exactly what this does. This one is red mixed with 10% yellow. Or I can even, let's mix yellow with a deep pink color. And you can see what happens here. It slowly goes to this nice pink. Imagine the possibilities when you use variables there instead of actual specified colors. And we don't just get these 3 adjusters. We get all these. We can adjust the red, green, and blue channels, the hue, saturation, and lightness, the whiteness and blackness, the tint, shade, and blend I already showed you. There's even a contrast adjuster that automatically makes sure that you get a color with sufficient contrast. And you can already have tint and shade in SASS, by just defining them, and then you can use them like this, which is a slightly better syntax, actually, but it's not the same that's eventually making it into CSS. These functions are already available if you're using Bourbon. And if you've ever used Photoshop, you probably remember that it doesn't support HSL. It supports another similar color system, which is called HSB. And until today, there was no way to specify to use the same system in CSS. HSB has many names. One of them is HSB, obviously. There's another one called HSV, and there's also HWB, which is what seems to be going to make it into CSS. But it's exactly the same color system as people are used to from Photoshop. So to recap, and there are a few more things that I didn't show, gray is going to become a function. We're going to get 4- and 8-digit hex codes. We're going to get a color function that's awesome and does all sorts of things. We're going to get HWB. Something I didn't show is that in HSL, you will be able to use named hues like yellow instead of 60 degrees, or angle values, which is basically using 60 deg instead of 60, which I'm not sure why is particularly useful, but I guess people made that typo many times that it had to make it into CSS. And like I mentioned in the beginning, RGB and HSL will accept alpha values, but that's one of the things that aren't exactly certain. Some of those things that I displayed about CSS Color Level 4, specifically the color function, you can use them with this new preprocessor called Myth.io. I haven't actually tried it, but it claims to support lots of CSS extensions in the way in the same syntax as draft specs. So it basically works as a polyfill. Variables variables in this preprocessor look exactly the same as the CSS variable specification. Same with the calc function that's actually supported natively these days. Color manipulation with the color function, so on. And before I finish, this is this is not exactly relevant to CSS, to color formats in CSS, but I see many times people develop tools and they accept input in CSS colors, and they try to parse every possible CSS color, but basically the only thing you need to parse is RGB and RGBA, because you can just create the dummy element and then read back its computed style and just parse that, which is always RGB or RGBA, at least in i9 Plus and other modern browsers. And a little note, as this presentation is nearing its end, RGB is not the only color space we have. There are lots of others. As we said, RGB is additive color, but that's not how we learned that colors work as kids. We learned that if we mixed, for example, yellow and blue, we would get something green, which is basically similar to how CMY works, which is why it's called subtractive color, because the three components together are supposed to make black. And this is similar to how printers work. However, the reality is that you can't exactly, printer inks are never this pure. This is just theoretical. In reality, when you mix magenta, cyan, and yellow, you get this dirty sort of dark gray, which is why we got another ink, which is why our printers use CMYK and not CMY. However, CMYK, even with the extra ink, has a smaller color gamut than RGB. And there are multiple different types of RGB. sRGB is the standard RGB, which has a rather small gamut, but there's also Adobe RGB, which is wider, and the whole thing is lab, which is all the visible colors that our human eyes can see. For example, you can't display fluorescent colors on a screen. Similarly, you can't display RGB aqua on a printer unless you're using Pantone colors, which increase the gamut much more. And also exactly because of this, converting between RGB and CMYK, and also converting between any two different color spaces is not trivial. There are many algorithms on the web that claim to convert CMYK colors to RGB and vice versa, and they do ridiculous things like converting aqua, which is RGB 0 to 155 to 155, and they convert it to CMYK cyan, which is basically this color, which is nothing like the RGB cyan. Which is why when you want to accurately convert between these colors, you need a color profile. And there are files for every color space, and it's the ICC color profiles are defined by the International Color Consortium, which is what ICC stands for, and that's basically the W3C of the web. And some of them have a curve to describe how how each color translates to the other color space. Some of them have a table because it's so difficult to convert between them with an actual function. So that's basically all of color science. You think that something is simple, and then you research it, and it turns out to be insanely complicated. For example, when I made this game that I showed you earlier, I wanted to show the color difference between the color that the user has typed and the color that you have to guess. And even today, the algorithm it uses is not great, because when I researched it, it turns out that there was an algorithm in 1976, and it was quite complicated, but it wasn't, even that wasn't accurate. And then they defined a new algorithm in 1994, and even that wasn't accurate. So there was another paper in 2000, and if you see the math for that color formula that came out in 2000, it's like a whole page of mathematical formulas just to calculate the difference between two colors. That's how deep the color rabbit hole goes. Everything you wonder about color, it ends up being insanely complicated. Even, I love color for years, and I think I barely know like 1% of it. So since we talked about different color spaces, before I finish, I want to try something which might not work, but colors are not just, when you think about colors, you probably think of colors displayed on a screen or colors displayed on paper or these sorts of things, but there are all sorts of different machines that can display color these days. For example, one of them is this little robot called the Sphero, which I stole from Julian, that's going to present the Nodecopter session and some other things about robots during lunch. So apparently you can connect this through Bluetooth, which I have to remove and then re-add. And then you can set the color on it with a node script. Unfortunately, currently it only accepts named colors, which are the same horrible named colors you get in CSS, and hex colors. But I still think it's quite cool how you can just specify, how you can just use code and specify a color for this. So let's set it to my favorite color, FF0066, which is this nice hot pink. Let's save this, and then let's run the node script again. If it works, half of the times it doesn't, and there it is. And I can even change it and make it into like an orange, which is red with some green, maybe a little more green, and zero for the blue. And then I need to stop the node script, because that's just something I did this morning. So the interface is not exactly intuitive. And then run it again, and if it works, we will see orange. And I thought it's quite interesting, especially since some colors look quite different than what you would expect, because it's a completely different, it has a completely different gamut from your screen or anything else. For example, if I try to display white, and I promise this is the last one because I know I'm running late. If I try to display white, you will see that it doesn't quite look like white, it looks like a light blue. So that's about it. I hope you learned something. Thank you very much.